Hello, everyone. In this video, I'm going to be going over problem 5 of chapter 14 in the Fundamentals of Mass and Heat Transfer textbook. This problem states that a helium and xenon mixture containing 0.75 mole fraction of helium is used for cooling of electronics in an avionics application at a temperature of 300 Kelvin and atmospheric pressure. We want to calculate the mass fraction of helium and the mass density, molar concentration, and molecular weight of the mixture. If the cooling system capacity is 10 liters, what is the mass of the coolant? So first things first, I like to write everything down. The molecular weight of helium is equal to 4.003 kilograms per kilomole, and the molecular weight of xenon is equal to 131.3 kilograms per kilomole. Now, both helium and xenon are gases. Specifically, they're noble gases. Pretty fun, very inert. What's the point of this? We can use the noble gas law in order to find the molar concentration of the mixture, which is pretty much in a unit volume, how many particles of any of the two elements are in there. The noble gas law, of course, being PV is equal to nRT, where P is pressure, V is volume, N is the number of particles there are, R is the universal gas constant, and T being temperature in units Kelvin. Since we want the molar concentration, we want N over V. So we rewrite this equation that C is equal to P over RT. The universal gas constant in this instance is going to be 8.206 times 10 to the negative 2 cubic meters times atmosphere over kilomole. This is specifically what the universal gas constant looks like with these units. It looks different depending on exactly which units you're using, atmospheres, bars, kilojoules, a lot of different ways to use it, a lot of different ways to look at it. Of course, doing all this will give us a molar concentration of 0.0406 kilomoles per cubic meter. Next up, in order to find the mass fraction of helium, first we want to find the molecular density. No, sorry. We want to find the mass density of the helium as well as the mass density of the entire mixture. We can find the mass density of helium using equations 14.1 right here and 14.11, combining them. 14.1 is just mass density of a gas. 14.11 just is all about percentages, since we know that helium is 75% of the helium is 75% of the mixture. So, we're going to combine those together. So we can then find that the mass density of the helium is 0.122 kilograms per meters cubed. And then in order to find the total mass density, we just take the mass density of the helium and we add it to the mass density of the xenon, and we can put the equation like this because they're both going to be using the exact same concentration, so we can take it out, which will give us a total mass density of the entire mixture of 1.46 kilograms per meters cubed. Now, if we just find the fraction of the mass density of the helium over the mass density of the entire mixture, we can find the mass fraction of helium in this mixture, which is 0.0838. That is the percentage of mass that the helium takes up. Yes, there is more helium in this mixture, but the xenon is just far more massive. It's just a far bigger atom than the helium, so it still takes up most of the weight. So next, we can very easily find the molecular weight of the mixture. That just is going to be equal to, once again, looking at equation 14.1, just reorganize that. It's going to be the total molecular mass over the total density. No, the total molecular mass or molecular weight is equal to the mass density over the concentration. We found the mass density. It's 1.46 kilograms per cubic meter. The C is the same C we've been using this whole time, 0.0406 kilomoles per cubic meter. Put that over each other, and we find that the molecular weight of the entire mixture is 35.8 kilograms per kilomole. Next, final part of the problem. We want to find the mass of the coolant. If the volume is 10 liters, well, guess what? We know the mass density, or just the density. We know the volume, 10 liters. This is just plug it into the standard density equation where rho, or the density, is equal to mass over volume. Rearrange it so mass is equal to density times volume, which is 1.46 kilograms per cubic meter times 10 liters. So as a general rule of thumb for the conversion, 1,000 liters fits into 1 cubic meter. So that's going to be about 100, not 100, like 0.01 cubic meters. I just plugged that all into my calculator, so I didn't see the actual volume in terms of cubic meters. But in the end, the final answer should be that the molecular mass of this whole thing is 0.0146 kilograms. Barely weighs anything. Makes sense with dealing with gases for the most part. But yeah, that's problem 14.5 in the textbook. I hope that this video was helpful, and I hope that the rest of the videos on this channel are equally as helpful. Thank you very much for watching.